Welcome back to the Deep Dive. Today we are moving past the usual headlines and going straight into a technical report that is quietly shaping the next 2 decades of how we move.
We're talking about the Intelligent Chassis Technology Roadmap.
Exactly. It's this incredibly detailed strategic document that lays out a vision all the way to 2040. And it's not just ideas, it's packed with quantitative goals, hard numbers that are meant to transform the automobile.
Right, to transform it from, a purely mechanical device into something much more dynamic and intelligent.
And this is so critical because for years, the whole conversation around autonomous driving and EVs has really focused on the brain and the eyes of the car.
The AI, the decision-making, and then the perception, stack lidar, cameras, radar, all of that.
But the intelligent chassis, the IC, that's the execution layers, the forelimbs of the vehicle.
It's the system that has to take a complex digital command, like steer 3 degrees right and brake at 0.5 G, and turn it into a precise physical action, instantly.
So this report, which reads with the kind of analytical rigor you'd expect from a major consultancy, really establishes the IC as the new strategic high ground.
It is. It's the new frontier in the global automotive race. And it's driving this huge convergence of different industries, electronics, control theory, advanced materials, you name it.
Okay, so let's unpack this. Our mission today is to define where we are now, map out the trends, and then get into those aggressive milestones for the tech.
And it's all in service of realizing the full potential of, autonomous driving and electrification. The big picture goal here is about converting an existing advantage in EV manufacturing into total leadership in intelligence.
And the source material really breaks down the strategic importance of this into 3 key parts. The first one is pretty immediate.
It is. The IC is the fundamental platform for any advanced autonomous driving, especially L4 and L5. It just won't work without it.
Without that instantaneous, precise, and this is key redundant control of braking and steering, the whole AD system just can't operate safely.
It can't. And second, the IC is the key carrier for maximizing the benefits of electrification. Things like advanced regenerative braking or lightweight chassis design, that's all executed by the chassis.
Which promotes safety, reliability, and of course, those massive carbon reduction goals that everyone's trying to hit.
Absolutely. And that leads to the third point, which is all about competition, looking out to that 2040 horizon.
Right. This is the next battlefield. The first race was about building the perception systems, the eyes. Now it's about who can build the best limbs.
Exactly. It's not just about making a better brake pedal. It's a total technological and industrial ecosystem shift. It's about who will dominate the future of mobility platforms, especially as we start thinking about modular vehicles.
Okay, so where are we starting this journey? The source material suggests this isn't a gradual evolution. It's a rapid, decisive move away from the traditional mechanical and hydraulic chassis.
It's a huge shift, and it's happening now. The starting point is the underlying EE architecture, the electrical and electronic backbone of the car.
For decades, that was a distributed system, right? Every little function had its own little computer.
Your door lock, your ABS module, everything was siloed. That is rapidly changing into centralized domain control.
And the consensus since around 2020 has been to fuse 2 of the most critical domains.
The power domain, so propulsion, energy management, and the chassis domain, which is your steering, braking, and stability.
Now, fusing those 2 sounds, frankly, a little risky. These are the most safety-critical systems in the entire vehicle.
It is a risk. It concentrates that risk, which is why the roadmap later puts so much emphasis on hitting the highest safety standards, ASLD. But the motivation, the upside, is just overwhelming.
What's the big advantage?
When you fuse them under a single high-performance controller, you can manage the vehicle's dynamic behavior holistically. You're not just managing functions, you're coordinating them.
So the system can use the electric motor to help stabilize the car during a hard braking maneuver, for instance.
Exactly. Coordinated control. That fusion controller becomes the absolute heart of the vehicle's regional architecture.
And that structural change is what allows for this really sophisticated fusion control that we're starting to see from both the big global leaders and some of the faster-moving domestic innovators.
We are. You look at players like Bosch or ZF, they're building these holistic vehicle motion control systems.
So instead of the brake controller acting on its own.
Right. The system gathers data from the entire vehicle and the environment and uses predictive models to optimize braking, steering, and the powertrain all together at the same time.
Bosch, for example, has really focused on integrated slip rate and torque control.
Yes, using these feed-forward control algorithms that are based on super accurate vehicle dynamics models, it makes things like ABS and stability control so much more effective, especially in extreme situations.
And we're seeing domestic innovators achieving parity, sometimes with these really high-tech solutions that leverage the unique architecture of an EV.
A perfect example is BYD's Yonggong system. This isn't just a fancier suspension, it's an intelligent vertical fusion
What
solution.
does that mean, vertical fusion?
It uses dual cameras and stereo matching to build a real-time 3D map of the road ahead. It sees the elevation, the roughness, the curve of the road.
So it can sense the vertical dimension, the bumps and dips, before the car even gets there.
Exactly. And with AI algorithms, it can then adjust the suspension before the wheel even hits the bump. It turns the chassis from a reactive system into a predictive one.
That's a huge leap. So it's not reacting after you hit the pothole, it's preparing for it.
Precisely. It gives you this incredible stability. The effect is often described as feeling like you're riding on perfectly flat ground, even when you're not.
And you contrast that with someone like NIO, who's focused more on domain consolidation.
Right. NIO developed their own intelligent chassis domain controller. They basically centralized the control logic for over 100 traditional components, suspension, active aero, shock absorbers, into one single unit.
Which means unified software control, lower latency, and way less hardware complexity.
It's a different path to the same goal,
Yep.
software-defined control.
And we see that same transition mirrored in the physical architecture of the car with things like CTC and CTB technology, cell-to-chassis or cell-to-body.
Correct. This is about more than just neatly packaging the batteries. It's about making the battery pack a structural, load-bearing component of the car.
And the goals there are twofold, right? Lightweighting for efficiency and a huge increase in torsional rigidity.
A massive increase. The quantitative goals in the source material for passenger vehicles are staggering. They're targeting a torsional rigidity of 55,000 newton meters per degree by 2040.
55,000. That number is enormous. To give you some context, a lot of high-performance sports cars today are somewhere in the 35 to 45,000 range. So why is that extreme stiffness so important for an intelligent chassis?
Well, it's not just about crash safety or reducing noise and vibration, though it helps with both. For autonomous driving, that structural rigidity is critical because it gives you a more stable and predictable platform for all your sensors.
So it minimizes the body flex and vibration that could throw off the LiDAR or the cameras?
Exactly. Less noise in the perception system. It also means more precise control because less energy is lost to chassis flex when you're making a dynamic maneuver.
But the analysis points out a huge constraint here. The design might be ready, but the manufacturing isn't quite there yet.
That is the critical bottleneck. The concept is mature, but scaling up the actual manufacturing equipment is a huge challenge. Specifically, you need these ultra-large-scale integrated die casting machines.
We're talking about machines with 9,000 tons or more of clamping force.
At least. And you need the specialized aluminum alloys to go with them to cast these huge single-piece components. Without that foundational heavy manufacturing, these amazing integrated designs stay as prototypes. The physical world has to catch up to the digital ambition.
Let's pivot to the core components then. The whole wire control revolution is the foundation for this. How ready are the key systems, braking, steering, suspension for this digital takeover?
They're all moving toward it, but at different speeds. For braking, the first step, electronic hydraulic braking, or EHB, is scaling super fast. It's forecasted to hit 100% assembly rate by 2025.
So EHB is mature. It gets the job done for basic wire control.
It does. But the real game changer is the next generation, electromechanical braking, or EMB.
This is the one that completely gets rid of all hydraulic fluid. It's purely electric motors and gears pushing the brake pads.
That's the one. And it offers incredible advantages in response time and control, but the report notes it's still in the pre-mass production phase.
What's the main hurdle holding it back?
Reliability and cost. It's a safety-critical system, so achieving the redundancy and durability you need under all conditions is just incredibly complex. The tech is competitive, but getting it from a prototype to a reliable, cost-effective part you can put in millions of cars is the challenge.
Okay, what about steering and suspension?
Steering is also moving quickly. Electric power steering, EPS, is already mainstream. The next step is steer-by-wire, or SBW, where you physically remove the mechanical steering column.
So there's no physical link between the steering wheel and the front wheels.
None. And that's nearing mass production. The big challenge there is all about safety redundancy. What happens if the power fails? And just as importantly, simulating road feedback. the feel of the road.
For those times when a human driver has to take over. And suspension.
Semi-active systems are already in mass production, becoming more common even in mid-market cars. But the fully active systems, the ones that can actually add energy to counteract forces, are much more complex.
Like electromagnetic active suspensions.
Right. The roadmap says those are still largely in the pre-research stage, especially for domestic component companies. That's a pretty significant technological gap that needs a lot of investment to meet the 2040 vision.
So with all this complexity, hardware, software, everything integrated, the old way of physically testing cars just can't keep up. What's the new paradigm for making sure these systems are actually safe?
The whole testing model is shifting to a digital AI-supported environment. We already have driver-in-the-loop systems that are helping reduce development time.
Where a human driver is interacting with a virtual car model.
Exactly. But the long-term strategic goal is to build these comprehensive, high-fidelity driving simulation platforms, true digital twins of the vehicle.
What does a digital twin of an intelligent chassis really mean? It sounds like more than just a 3D model.
Oh, it's much more. It includes incredibly detailed, verified physics models of the braking, the steering, the suspension, the tires. Everything has to accurately reflect the real world.
And why is that so essential?
Because it lets you break the limits of real-world testing. Think about those long-tail safety events, the really rare but critical scenarios. You can't drive millions of physical miles hoping to encounter one.
But in a simulation, you can create it on demand.
And you can run it a million times overnight. The future is leveraging large AI models for this virtual testing, for scenario generation, for data optimization. It allows engineers to test, learn, and push over-the-air updates to the chassis systems safely.
If we connect all this detail back to the bigger picture, the 2040 vision isn't just about building a better car. It's about something much more holistic.
It is. It's about establishing a globally dominant industrial and innovation ecosystem. It's about fundamentally redefining mobility itself.
And that vision is captured in this really powerful slogan: low carbon, high efficiency, zero casualties. How does the chassis as a piece of tech actually deliver on those three principles?
Through continuous evolution, low carbon is addressed through lightweight components and, crucially, maximizing regenerative braking efficiency.
So using the electric motor to recapture as much energy as possible.
Right. Zero casualties hinges completely on the active safety controls that are enabled by the precision and redundancy of wire control systems like EMB and SBW.
And high efficiency seems to be about more than just energy consumption. The source links it to entirely new forms of mobility.
Exactly. High efficiency in this context means modularity and reconfigurability. The ultimate ambition is to enable what the report calls stereoscopic transportation.
Multi-dimensional movement.
Right, which means the IC has to evolve to be modular enough to potentially support things like low-altitude flight mechanisms. The vehicle becomes a universal mobility platform, not just a car.
So the end goal of this whole roadmap is to create this globally leading cluster of IC innovation and industry. And to get there, the source lays out a very structured three-phase path.
This three-phase roadmap is really the backbone of the whole strategy. It guides the industry over a 15-year horizon, from basic component breakthroughs all the way to full service-oriented functions.
Okay, let's break that down. Phase I is the near term, 2026 to 2030. This is all about laying the groundwork for L4 autonomy.
Phase I is technical breakthrough foundational L4 support. The core focus is getting those key components right. Mastering EMB, stabilizing SBW, and developing viable active suspension actuators. This is about building the technical foundation.
And there are hard targets for this phase.
Very aggressive ones. The assembly rate for these integrated IC systems has to be over 30% for passenger vehicles and 60% for commercial vehicles. And the whole system has to be robust enough to support Level 4 intelligent driving.
So that's the groundwork phase. What comes next in the midterm?
Phase 2, from 2031 to 2035, is product innovation, cross-domain fusion. Once the components are mature and cost-effective, the focus shifts to integration and creating new products.
Like those highly integrated wheel-side driving units we talked about.
Exactly. And you'll see deep cross-domain fusion maturing. Power, chassis, cockpit, and AD systems won't just be communicating, they'll be completely codependent.
And the assembly rate targets jump up again.
They do, over 60% for PVs and 70% for CVs. And this phase is explicitly designed to support Level 5 intelligent driving across all environments.
And then the final phase, the long-term vision from 2036 to 2040. This is where the truly futuristic, reconfigurable vehicle emerges.
Phase 3 is functional servicization, ecological reconstruction. This is the end state. The main goal is achieving what's called functional servicization.
What does that mean in practice?
It means the IC components are fully modular, standardized, and they function like scalable, interchangeable services, almost like apps on your phone.
And the assembly rate is over 80% for both PVs and CVs.
Right. And the technological output is support for that multidimensional mobility, including the final implementation of the upper and lower split chassis architecture.
The skateboard and pod concept.
Exactly. And this phase also sees the full realization of large AI models driving the entire development and testing tool chain.
Let's really drill down on that first phase, though, because hitting those 2030 targets is absolutely critical. These are the benchmarks that define L4 safety and performance.
They really establish the technical barrier to entry for the industry. On the safety side, all critical systems braking, steering, power must achieve the highest possible rating, functional safety level ASIL-D.
For our listeners who might not be deep in automotive safety standards, what does ASIL-D actually mean for the person in the car?
It's about the probability of a catastrophic failure. ASIL-D requires that a failure that could cause severe or fatal injury happens no more than once in every 100 million operating hours.
100 million.
It basically means the system has to be designed with so many layers of redundancy and fail-safes that the risk of a malfunction causing serious harm is negligible. And achieving that for a fully software-controlled chassis is a monumental engineering task.
And beyond safety, the performance benchmarks are just as aggressive. The ELK test speed, for example.
The ELK test, that emergency lane change maneuver, is a key measure of obstacle avoidance. For a typical B-class passenger vehicle, the target speed is 85 kilometers per hour or more by 2030.
And to hit that speed in a fully automated maneuver requires perfect coordination.
Perfect VLL vertical, lateral, and longitudinal coordination. It needs instantaneous steering response and incredibly sophisticated tire modeling, all driven by that central IC controller. It's a signal of true mastery over the vehicle's dynamics.
That's an incredible performance metric, and it connects directly to the power delivery side as well.
Absolutely. The RoadMap also sets targets for regenerative braking. The electric motor's maximum deceleration capability has to be at least 0.8 G.
So the system is reliably using the motor itself as a core part of the braking system, not just the friction brakes.
Exactly. It's using electrification as a fundamental component of vehicle safety and stability.
And the redundancy requirements are just as tight. That cross-system redundancy switching time of under 100 milliseconds. That sounds incredibly difficult. What's failing that it needs to switch so fast?
The 100 millisecond target, a tenth of a second, is the maximum time a backup system can take to kick in. It could be a failure in a communication bus, a sensor input, a power relay.
And that super fast switch ensures the L4 system stays in control without any noticeable jerk or loss of stability for the passengers.
Precisely. It's a huge factor in preventing motion sickness in autonomous vehicles, which is a real concern. This whole first phase is just laser focused on mastering those core components and getting that VLL integrated control right.
Okay, this is where it gets really interesting for the consumer, because we're moving from these broad strategic goals to the specific high-tech features that are going to completely change the experience of driving or riding in a car by 2040.
We're talking about the complete dissolution of the traditional chassis as we know it. It's being reconstituted into these highly integrated digital modules. We're moving toward what's called the integrated driving unit concept.
And this is where you package everything at the wheel.
Everything. The drive motor, the brake actuator, the steering mechanism, the active suspension, even intelligent tire functions, all in a single, compact, wheel-side module.
The implications of that are profound. We're not just talking about moving forward and backward anymore.
Not at all. When you can control every motion function at each wheel independently, you unlock capabilities that are just impossible today. We're already seeing prototypes with four-wheel independent 360-degree turning.
The so-called crab walk, where the vehicle can move sideways or diagonally.
Exactly. It completely transforms parking and low-speed maneuvering. The RoadMap is betting that this integrated unit becomes the industry standard.
But the performance targets for this unit are pretty tough, especially when it comes to speed and managing weight.
Now, 2035, these integrated units have to achieve a maximum travel speed of at least 150 kilometers per hour. And that's a huge engineering challenge because putting all that hardware at the wheel adds a lot of unsprung mass.
Unsprung mass being the weight that isn't supported by the suspension. And more of it is generally a bad thing for ride and handling.
It is. So hitting 150 kph while managing heat and maintaining stability with all that extra mass requires major breakthroughs in materials and active suspension compensation algorithms.
Let's circle back to braking, because EMB is the critical next step. The precision requirements for 2040 are just mind-boggling.
The move to EMB is non-negotiable for L5 autonomy because it gives you that granular, instantaneous control at each wheel. By 2040, the system response time has to be 80 milliseconds or less, from 0 to max braking.
And the control accuracy is less than or equal to 0.1 meters per second squared. What does that accuracy mean in human terms?
It means the system's ability to hold a desired rate of deceleration is virtually perfect. For an L5 system making micro-adjustments in high-speed traffic, that precision is what allows it to perfectly coordinate braking and steering to avoid a collision. It eliminates the tiny errors that can build up into big risks.
And beyond just stopping, there's that incredible efficiency target for regenerative braking.
By 2035, the target for energy recovery efficiency from motor braking is 90% or more.
90%. That is incredibly aggressive. You're capturing and converting 9/10 of the kinetic energy back into battery power.
And doing it seamlessly so the occupants can't even feel the transition between regenerative and friction braking. And performance-wise, this motor braking has to be able to deliver a full 1.0 G of deceleration.
A big step up from the 2030 target. And this all ties into the steering side, where steer-by-wire needs similar leaps in precision and redundancy. The target for steering error is astonishing.
It is. Reducing the steady-state steering error to just 0.1 degrees by 2040.
Flawless wire control. How do you even manage that level of precision over the 15-year life of a vehicle? You'd have to worry about sensors drifting out of calibration.
You do. It requires constant self-diagnosis and calibration using sensor fusion to cross-reference everything. But just as critical is the redundancy switch delay. If your primary steering motor fails, the switch to the backup has to happen in 10 milliseconds or less by 2040.
10 milliseconds. That is literally faster than you can blink.
It has to be functionally instantaneous. Any perceptible delay in steering control at highway speeds would be catastrophic. This is the level of performance you need to meet the demands of new safety frameworks, like SOTIF.
You mentioned SOTIF safety of the intended functionality. Can you expand on that?
So ASLD covers hardware failures. SOTIF addresses safety issues that happen when the system is working as designed, but encounters a situation it wasn't prepared for.
Like a sensor being blinded by sudden fog?
Exactly. The IC system has to be aware of its own functional limits and be able to execute a safe maneuver, a minimum risk maneuver, when it hits those limits. It needs self-awareness.
And all this precision feeds into that overarching control philosophy. VLL fusion control, moving in 3 dimensions.
Vertical, lateral, and longitudinal. You're integrating the motors, steering, and active suspension to manage the vehicle's entire motion attitude, not just react to inputs. The goal is to improve the vehicle's controllable movement boundaries, its dynamic envelope, by up to 10% by 2040.
Improving the dynamic envelope by 10% means the car can brake later, corner harder, recover from slides faster. It's a fundamental redefinition of performance.
It is. And underpinning all of it is extreme redundancy. Let's go back to that brake failure scenario. By 2030, a single brake failure still has to leave you with half a G of deceleration.
Which is a decent safety buffer.
But by 2035, that has to double to 1.0 G.
To put that in perspective, if your main brakes fail completely, your backup system needs to be able to stop the car as hard as a high-performance sports car stops under maximum effort.
Exactly. That's what builds confidence in L5 autonomy. And by 2040, the goal is even higher. Redundancy braking capability should not degrade at all, and the system's ability to diagnose a failure has to hit 99.9%.
Near perfect diagnosis.
It's required to keep the system ASLD compliant for its entire life.
And the capstone for this 2040 passenger vehicle vision is the architecture itself becoming reconfigurable. The upper and lower split chassis idea.
This is the ultimate flexibility play. Once the chassis is fully wire-controlled and modular, you can, in theory, separate the upper body, the cabin, from the lower chassis, the motion platform.
The ski port in the pod.
Precisely. The lower chassis becomes this universal self-propelled platform, and you could swap out the upper body for a cargo unit, a passenger drone mechanism, whatever you need. This is what enables that stereoscopic transportation vision. The chassis becomes a dynamic, service-driven system.
That brings up a really important question. Why does the RoadMap track commercial vehicles, or CVs, separately. They have different timelines and different metrics.
It really comes down to fundamentally different priorities. It's all about payload, the specific mission, and just the harshness of the operating environment.
Right. With passenger cars, it's often about the driving experience. For CVs, it's about load capacity, uptime, low energy use, and getting L4 and L5 autonomy working in very specific contained scenarios.
Fixed freight lines, public bus routes, things like that. The sheer mass and the number of operating hours demand completely different solutions. Architecturally, CVs are focused on large, bottom-mounted battery packs that can be easily swapped for maintenance.
The braking systems are a great example of the divergence. Passenger vehicles are going to pure EMB, but for CVs, the roadmap suggests electro-pneumatic systems, EBS, will coexist with EMB for a long time. Why keep air brakes around?
Because heavy trucks need a phenomenal amount of sustained stopping power. Air pressure is just a proven, powerful, and durable way to get the clamp force you need for a 40-ton rig.
So EBS, which is electronically controlled air brakes, is mature and it's being improved.
Exactly. The roadmap says both systems have to get faster. EBS response time needs to be under 200 milliseconds by 2040 and EMB under 160.
And the force required from the EMB systems on trucks must be incredible.
It is. The target is a clamp force of 180 kilonewtons or more by 2040. That's what you need for an autonomous system to have absolute control over stopping a fully loaded trailer on a downhill grade.
And the steering has to handle that same massive load with L5 precision.
It's all about high-torque steering. Wire-controlled steering for CVs needs to be able to output at least 8,500 newton-meters of torque.
And that's not just for tuning the wheels when you're stopped. It's for the tiny micro-adjustments an L4 computer needs to make on the highway.
Right, and it has to do it with a response delay of less than 30 milliseconds by 2040, even when it's controlling multiple axles or a trailer connection.
And given the high center of gravity on these vehicles, the suspension goals are all about stability and preventing rollovers.
Stability is everything. It's about safety and profitability. The roadmap sets a very specific goal. In an emergency lane change, the anti-rollover angle must be 2 degrees or less by 2040.
That requires highly specialized active suspension focused purely on keeping the load stable.
It does. And suspension height control accuracy is targeted at 5 millimeters or less, which makes automated tasks like hooking up to a loading dock or a charger much more efficient.
For L4 and L5 in commercial vehicles, the control is focused on preventing rollovers, but there's this massive emphasis on operational efficiency through something called health management.
This is where the real money is for logistics. The uptime of a commercial fleet is directly tied to profit and even the stability of the national supply chain. So while VLL control is about preventing rollovers and jackknifing, the real economic game changer is health management.
What are the key metrics for that? What's the goal by 2040?
The goals are extremely ambitious. The systems are aiming for 95% accuracy in predicting the lifespan of wear and tear components.
95% accuracy. That's not just better maintenance planning. That could mean achieving zero unplanned downtime.
That is the goal. And it's supported by specific monitoring targets, like 98% accuracy for monitoring oil and other fluids.
So this all relies on a cloud-based AI that's constantly learning from the entire fleet's operational data.
Exactly. It's about forecasting failures weeks or even months in advance. The ultimate objective is maintenance-free operation, driven by this deep integration of vehicle cloud data analysis. For a fleet operator, getting rid of unexpected stops is the difference between profit and loss.
So what does this all mean? We've laid out this incredibly aggressive national-level tech push with some just astonishing goals for 2040. But the source material, like any good analytical report, is very clear about the risks that could completely derail this whole vision.
It is. And we can group those risks into 3 major challenge areas: core technology bottlenecks, industrial collaboration deficiency, and foundational capacity shortfalls.
Let's start with the tech itself. We talked about EMB and steer-by-wire as these key enablers, but their immaturity also makes them the biggest technological roadblocks, right?
They represent a huge financial and engineering risk. Scaling them up still faces major hurdles with cost and reliability. EMB is just expensive to make at scale, and proving its long-term reliability is still a work in progress.
You have to convince everyone that an all-electric brake system is as trustworthy as the hydraulic systems we've used for a century.
Exactly. And for steer-by-wire, the challenge is less about raw mechanics and more about the complexity of the control system.
You need to have enough backup systems to guarantee that ASLD safety level And you have to get that road feel simulation just right.
That's right. And there's also a major bottleneck in high-performance active suspension actuators and the complex algorithms that run them. A lot of that advanced tech is still reliant on imported components.
The second area is industrial collaboration deficiency, the fragmentation issue.
This is a classic systemic problem. When you move to this centralized cross-domain fusion model, the complexity just explodes. You have 5 different suppliers building these incredibly sophisticated proprietary modules that all have to talk to each other instantly and flawlessly.
So the report stresses an urgent need for standardized interfaces and protocols.
It does. Without unified standards, you get vendor lock-in, which drives up costs. But more importantly, it slows down the whole development cycle because engineers are spending all their time just trying to get these different systems to communicate. It creates friction.
And finally, there are the foundational capacity shortfalls, the core industrial infrastructure. This seems like an overlooked, but potentially huge strategic vulnerability.
This might be the most critical long-term weakness the analysis identifies. The report flags 3 areas of dependency. First, the lack of domestic, high-performance, chassis-specific computer chips.
These safety-critical systems need specialized, reliable processing power.
And if you're reliant on imported high-end chips, you have a massive supply chain vulnerability. Second, the manufacturing capacity itself.
The precision equipment you need to actually make the parts.
Exactly. The high-end processing equipment needed for the actuators and sensors and EMB and steer-by-wire. If the tools you need to make the parts aren't domestically produced and controlled, your whole strategic vision is at the mercy of global trade dynamics.
And the third weakness is in the digital foundation itself, the software.
Yes. There is an urgent need for high-accuracy dynamics simulation software and verified databases, those digital twins we talked about. If your simulation software or the data you use to train your AI is incomplete or inaccurate, the system you build might look great on paper but fail in the real world.
So what's the strategic outlook here? The call to action seems to be a major push toward vertical integration and full-stack solutions to bridge these gaps.
The conclusion is that the intelligent chassis really is the decisive point for the future of the auto industry. The trends wire control, fusion, intelligence are irreversible. And to convert that existing advantage in electrification into true leadership in the intelligence era, the industry has to adopt a much tighter, more integrated model. It has to tackle the full stack from the silicon chip all the way up to the control software and the verification tools.
Okay, we have just done a massive deep dive into the intelligent chassis roadmap, dissecting a strategic plan that stretches out for 2 decades. Let's just recap the incredible scale of this. We talked about that irreversible shift from mechanics to full software control.
A shift that enables coordinated movement in 3 dimensions: vertical, lateral, and longitudinal.
We highlighted some astonishing quantitative goals, hitting the highest functional safety level, ASLD, across the board, and driving redundancy switching latency down to under 10 milliseconds for critical steering systems.
And that knowledge is really only valuable if you understand and apply it. The transformation of the IC is foundational because it is the executor system. It's what enables that ultimate goal of low-carbon, high-efficiency, zero-casualty mobility.
It's the chassis transcending its traditional role. It becomes this comprehensive service provider that defines the car's safety and dynamic ability in the age of autonomy.
By becoming this fully modular, reconfigurable piece of hardware that's coupled with an AI-driven, self-evolving software platform.
And we saw how this all culminates in that 2040 vision of functional servicization, where the whole vehicle platform becomes modular, supported by that upper and lower split chassis architecture.
Which is what structurally enables that dream of stereoscopic transportation, multidimensional mobility.
The platform itself evolves beyond just the road.
It becomes a multimodal mobility resource. It's a platform built for services, not just for driving.
Which brings us to our final provocative thought for you, the listener. We've focused almost entirely on the traditional auto industry. But if the end goal is a fully modular, reconfigurable chassis that can separate the body from the mobile platform, turning the IC into a rolling AI-governed mobility resource, what non-automotive industry do you think will be the first to truly capitalize on it? Think about package delivery, urban logistics, public transport, or maybe even municipal infrastructure. Who benefits most from a system that has zero unplanned downtime and is inherently multimodal? That might be where the real disruption begins.